Okay, we're just out for today. All right, so throat is a bit bad, so I can't really speak too fast or too much at once. I need to give my throat a break sometimes. I don't know whether there's this flu bug going around in school. So I have I just got the very bad sore throat. Although I think I'm cursed with sore throats. Like it hurts when I swallows like. Yeah, okay, but anyways, okay, so today, right, we're going to be touching on Gaseous State, part 2. So last lesson, right, let me just show you guys overview first. Okay, first thing we did last lesson was the ideal gas equation. And ideal gas equation is about an ideal gas. Do you think an ideal gas exists? No, because it's ideal, right? Okay, it's not real. So today, what we'll be discussing are real gases. Okay, in other words, what distinguishes an ideal gas and a real gas? Okay, we have to look at a few properties first. Okay, an ideal gas don't exist, so they're all solely based on assumptions. Assumptions that are obviously not true in real life. Right? So today, right, I just need to write everything on the white blank piece of paper because I feel that I'm going to go through in more structured manner. The notes are not wrong. Okay, but it's just that I feel that I think it's a bit better, more cohesive. Go through what I'm gonna write before. Okay, so in other words, right, okay, let's look at some assumptions. Okay, what are assumptions? Okay, basically, right, we have an ideal gas. And an ideal gas doesn't exist, so the assumptions are a bit unrealistic as well. You see it. Okay, but on the other side, right, we've got real gases as well. Okay, which is basically what we're going to do today. Okay, it's a step up from what we did last lesson. Last lesson was pretty much just solely on ideal gases. So because it's ideal, right, the equation can be very simple. Okay, just PV equals nRT, just start and inside. Okay, there's no more calculations for today's lesson. It's purely conceptual. All right, so anyways, the first assumption is also mentioned. Okay, but reading it alone is not enough. Okay, so I will need to explain this. Okay, the volume of the molecules, the gaseous molecules, okay, is negligible compared to the volume of the container. Okay, so this statement alone, right, has a lot of misinterpretation. Okay, the first problem is that people don't really understand what's the significance of this last part of the sentence compared to the container. Okay, you understand, right? The container contains air, okay, or just gas molecules. Okay, so when we say the volume of molecules is that, okay, an easy way to understand this is that an ideal gas has zero sign. Okay, which goes against our intuition because we know, right, that particles matter since primary school, right? We know that they must occupy some sort of space, right? They must have some sort of size. Okay, but in an ideal scenario, the gas molecules have no size. I know it's hard to fathom. Okay, but later you'll see more examples. Okay, so if they have zero size, right, it means do they occupy space? No. Okay, so that's the idea. They occupy no container space. So what does it mean when you occupy no space, right? Okay, I know it seems weird, okay, but later we will compare it to a real gas and make a bit more sense. Okay, so on the other hand, a real gas has significant volume. So the volume of molecules is significant compared to the volume of the container. Okay, so the opposite of the word negligible. Again, we need to use the word significant. And you cannot be lazy, right, and not write the words compared to the volume of the container. I feel that a lot of people get lazy and don't write that, okay, which is wrong because the whole interpretation will be incorrect. Okay, but anyways, okay, to make this a bit easier for us, real gases have sign, right? Okay, clearly it's some sort of sign. So do they occupy container space? Yes. Okay, so later we shall see what the significance of this is. They occupy container space. So once again, you must picture, right? We have a container, inside it contains gas molecules. It's all relative because we keep comparing to the container. Here you see the bit. Okay, so the next one, the next assumption is that it has negligible intermolecular forces. Okay, so take note of this. Intermolecular forces between molecules, okay, is negligible. Now, first of all, you must specify the words between molecules because if you don't, then it's not specific, right? So this is quite obvious because we know in chem bonding, right? Two particles, two molecules, do they have attractions with each other? Answer is always yes, right? Okay, but in an ideal world, right? In an ideal gas, there's no attractions. Meaning to say, right? If let's just say there are two molecules here, they won't attract each other. They're just vibing separately. Okay, for some reason this happens, yes. Okay, but of course we know that this assumption is wrong because it doesn't work like that. Right? Okay, so this. Oh, then on the other hand, real gases obviously have significant intermolecular forces. So you tell me this. Intermolecular forces between molecules is significant. So yeah, once again, the keywords are negligible versus significant. So let me just summarize again. An ideal gas, which is not real, doesn't exist. It has no sign and no attractions, which is weird because we know that in real life it has signs and it has attractions. Okay, so we get that out of the way first. Okay, so this is just to introduce the idea of fake gas. Okay, but now like we take a look at some conditions. How do some conditions alter the way gases behave? Some gases may be more towards the ideal side, or some gases will be more towards the real side. Okay, so how do we compare? The first condition that we need to take a look at is pressure. Okay, so we will be asked to discuss conditions. So we know that your pressure can be high, can be low. Okay, how does this affect the behavior? Does it become more ideal or less ideal? Right. So first things first, we have low pressure. Now, when it comes to pressure, right, we need to specify something. Low pressure, I'm referring to external. Okay, what does external pressure mean? So you think about the balloon. The pressure that you squeeze on the balloon, that is the external pressure, not the inside the gas pressure. So take an external. Okay, so what do we deal with here? Of course, the other variable, other condition is when you high external. Okay, so let's see how this works. Okay, I want you to draw a diagram, which helps us a little bit. So imagine this, imagine like a container that you can change the size of by pressing the outside. The outside is basically your external pressure. So if you have low external pressure, you're not pressing on the outside that much, right? So the gas molecules are, let me just draw 4 gas molecules. They're just like surrounding the container that it is in. Okay, but then on the other hand, we have high external. So do you realize that if you exert a lot of pressure, that's going to squeeze it very small, right? Okay, then what's going to happen? The same 4 gas molecules is going to occupy this space here. So let me just look at the 2 diagrams here. Okay, can get it so far, right? I just need you to tell me, right, which scenario does the volume occupy a more significant of the container? Again, it's always of the container. Yes, this one. Can you see the 4 same size? Again, both of them, the gas molecules are the same type, but this one occupies a greater space in the container, right? This one occupies a lot less. Now, the analogy is this. Okay, imagine, right, there's just 2 of us in this classroom. Are we occupying a lot of space in this classroom? Not really. Okay, not much. There's a lot of empty space there. But let's just say the walls of the room start closing in such that the 2 of us are going to be squeezed together. Or you can think of it this way. Imagine both of us, instead of being in this classroom, we have to squeeze in the toilet. Okay, are we occupying a lot of space in the toilet? Yes. So the idea is that it depends on the container itself. You need to always compare to what container you are in. High external pressure, you're going to occupy a lot of space in the container. Low pressure, you're not going to occupy that much space like in this classroom here. Makes sense, huh? So try to think of an analogy like this. And in other words, what I want to talk about is, can I ask you one? Which one the volume is negligible? Again, this one. So is the gas behaving more ideally or less ideally? More ideally. Okay, so that's what we do. So your explanation will look something like this. Okay, the volume of the molecules, or you can just say the gas molecules occupy a larger portion of the container. This whole thing of it. Molecules occupy a larger portion of the container. So, oh sorry, this one is smaller portion like that. Okay, the larger portion is that one. Okay, so this one occupies a smaller portion of the container, which means the volume of molecules is negligible. Okay, but once again, you must always compare to the container itself. In other words, okay, this makes the gas more ideal. But on the other hand, when you have a high external pressure, the molecules occupy a way larger portion, right? So that means the volume has to be, what's the word that we need to use? Significant. And if your volume is significant, that means the gas behaves more ideal. Yes. Less ideal, because it's going towards a real gas. Okay, so that's ideal. There's how many molecules occupy a larger portion of the container. Okay, In other words, it has significant volume. Okay, so significant volume compared to the volume of the coin. Again, right, by changing the conditions, we can have different behavior of the gases. Some gases will be more ideal, some gases will be less. So if the volume is more significant, is the gas more ideal, less ideal? Less ideal. Okay, so in other words, if you want the gas, right, to behave more like an ideal gas, you have to make sure that the external pressure is low. Let me just tell you what we're doing. Just write down everything on the board on this piece of paper. Because what we're going to do, right, is the notes are not wrong or anything, but I feel that this is a lot more structured. Okay, so once again, just to summarize what we've done so far, today we are discussing ideal gases and real gases. Ideal gases don't exist, real gases do. So they have different assumptions, and as you can see here, different conditions might affect these assumptions. Yeah. And then with that said, okay, we need to move on to the second condition, which is, I think, a lot easier to understand. Because remember, this volume idea is a bit spectral. It's relative. You can see that, right? Okay, so the next condition that we have is temperature. Okay, temperature is a very simple idea because this one, right, you have learned this in physics as well. Okay, but once again, we have high temperature and low temperature. So, can I ask you guys, right, when you change the temperature of a gas molecule, what also changes? What property of the gas changes? Not pressure, not really. Okay, in this case, we talk about, sorry, not really density. Okay, the molecules move a lot faster when there's a higher temperature, right? When the speed of the molecules moving is referring to its kinetic energy. Okay, good. So basically, the first thing I need you to think of, whenever you talk about temperature, right, for this case, you have to be directly proportional to the kinetic energy. The higher the temperature, higher the KE. The lower the temperature, the lower the kinetic energy. So it's basically the speed. Okay, so I ask you guys, at high temperature, obviously the kinetic energy is high, right? So let me ask you guys a simple question. Okay, if your molecules are moving all over the place very, very quickly, very chaotically, do you think they have time to form intermolecular forces with each other? No, cannot, right? In other words, your kinetic energy is a lot larger, it's a lot more significant than the intermolecular forces. Right? Okay, just imagine them moving so chaotically, so they have no time to form intermolecular forces. So can I ask you, right, are the intermolecular forces negligible or significant? Negligible, because they can't form any intermolecular force, right? So you can now tell me, the intermolecular forces between molecules is negligible. In other words, the higher the temperature, the molecule becomes more ideal or less ideal? More ideal. So once again, different conditions can affect the behavior. Some may be more ideal, some may be less. Then you just need to repeat the same thing for the other side, right? Okay, so when you have low temperature, what also happens? Okay, good. So you now can imagine, right, that the molecules are moving very, very slowly. So if they're moving very, very slowly, what can now happen? Okay, now they can form intermolecular forces with one another, right? In other words, the KE is not as significant as the intermolecular forces. In other words, are the intermolecular forces now significant or negligible? Significant. Okay, so you just process this idea. I think the intermolecular force one is very simple. Okay, the difficult one was what we went through just now. Okay, more of the volume occupation. Okay. Since the intermolecular forces are significant, the gas behaves more or less ideal. Yes, less ideal behavior. That's pretty much the idea. Right? Let's try something. See whether I can use my microphone for earpiece. No, I can't hear my ear. Okay, let's see whether this works. Microphone. Hi. Oh, goodness. Okay, let's see whether this works. Hello. Testing. Wait. Okay, so any questions so far? All right, okay, so what we have got for this few, then we are putting one earpiece in my ear. I can only hear half of myself. Okay, so hopefully the recording can hear me now also. Okay, but either way, right? Yeah, okay, this is what we have so far. Okay, this is the easy part, okay, because we are looking at conditions. Conditions very easy to fathom, right? Pressure and temperature, okay, quite simple. Okay, but what I'm going to be talking about now, right? Okay, just Richard, you might want to take a picture of this first, because I'm going to move on to the next segment. Yeah. Okay, so you can turn over to the next page or whatever, find some empty space, because now I'll be looking at graphs. Okay, the graphs are a lot more important here. Okay, so let's just see, right? So what we've done so far are conditions. If the question asks you for assumptions, don't tell me about the conditions. Okay, this one is a very common problem a lot of people face, right? Assumptions, just list down the assumptions. Okay, conditions, they talk about pressure or temperature, depending on what the question wants. Okay, but for now, then we take a look at the next part. Okay, so what's this next part here? Okay, we're going to look at deviations. Okay, this part a bit more challenging. Deviations of real gases. Okay, so today, as I mentioned already, right, our focus is on real gases. So yes, I compared to ideal gases, but different types of real life gases will have different behavior as well. Some gases are more ideal, some gases are less ideal. Okay, so let's take a look first, right? What I want you guys to draw is a graph. Okay, so just take a look at this graph here. Okay, I want you all to first look at the axis. Okay, we discuss this slowly. Okay, this is a very common graph that you end up seeing. Okay, and we've actually done this graph last lesson. Okay, last lesson we talked about a few graphs. We take a look at this. Okay, so can you all see something first? Okay, when we play with the PV equals the nRT equation, what's going on here? Okay, you all notice, right? Okay, first of all, we assume that the number of moles is the same, right? Then we shift everything else to the other side of the equation. So it looks something like this. PV over RT equals the number of moles. Okay, just a rough sketch, Number of moles is constant, right? Because that's our assumption here. So this entire thing is a constant. So can I ask you guys how the shape of this graph will look like? How does this graph look like in terms of its shape? Like that is constant. This value, this fraction has to remain constant. So the shape should be horizontal. Okay, so a horizontal line should look like this. So draw that in, and I want you all to take note, right? This is only applicable to an ideal gas. Because as we mentioned, this is an ideal gas equation. So obviously, it only applies for ideal gases. We know an ideal gas will never exist. So you'll never ever see a straight line in your life, right? So for this segment over here, I aim to go through two things. First, I want to compare the deviation of different types of real gases. Okay, then afterwards, later we will explain the shape of the graph. So I want you to draw two curves over here. An ideal gas is a horizontal straight line, but a real gas looks something like this. Okay, so I'm going to use CH4 as an example. We all know CH4 is a real life gas, and it looks like that. As you can see, you should know what's the meaning of deviation now, because it's deviating from the straight line, right? Hello? And then the other one, which is NH3, I need you all to draw it like this. Okay, so draw these two curves first. You have to go downwards before going upwards. Again, later then I'll discuss the shape with you guys. Now we are just comparing who deviates more. Okay, so far? Let me emphasize, both of them are real gases, but we're comparing who deviates more. So can I ask you guys, in this graph here, who deviates more? NH3, because it's always with respect to the straight line, right? So if NH3 deviates more, what does that mean? NH3 is less ideal or more ideal? Less ideal. You can see that? Okay, so I want you all to write down this question. Why is NH3 less ideal, or in other words, it deviates more, right? Okay, then CH4. So this is a common question in the exam. Okay, how do we discuss such question? Okay, so I want you to think through this, right? Okay, we have two different real gases, and again, whether they are real or not, we need to discuss these two properties, right? Okay, how real they are, the volume and the intermolecular force. Okay, guys, let's look at volume first. Can we compare the volume of these two molecules? Okay, if I ask you to compare the volume, right, what will you look at? Okay, NH3. How big or how small the molecule is depends on this one. You must look at the MR, right? Okay, so I ask you all, the MR of NH3 is what? Okay, so I just spare you all the calculation. NH3 is 17, CH4 is 16. Is there a way for us, is it good enough for us to compare volume in these two cases? No, okay, because 17 and 16, right, it's really not that significant. Okay, so for this particular question, right, we are not going to compare volume. Why not? We compare intermolecular forces. Now, we know that NH3 is less ideal. The volume is not that big of a deal. Okay, but that means it has to be due to the intermolecular forces. So guys, remember, this is some chem bonding concept. How do we compare the intermolecular forces of two gases? Electrons, sorry. Okay, electronegativity is not. Okay, remember, when it comes to intermolecular forces, the very first thing I want you to compare is the electron cloud size. Okay, so can we compare size in these two for these two guys? One is 17, the other is 16. Do you think size plays a big role here? No, not really. Okay, so we don't compare size. If you can't compare size, what we talk about instead? Okay, so remember the flow, the types of intermolecular forces. Why not we try this? Okay, so NH3, what's the intermolecular force? Hydrogen bonding. Okay, good. How about CH4? Oh, PD, sure. Okay, no, it's not. Because remember, how to compare type of intermolecular force? Okay, you must first ask yourself whether it's polar or non-polar, right? Okay, if it's non-polar, what intermolecular force is it? IDID. If it's polar, it could be what? Okay, PD or hydrogen bonds. Okay, in this case, right, NH3 fulfills the criteria for hydrogen bonding. So that's the answer. CH4 is non-polar. Remember, CH is non-polar bond. So it has to be IDID. Okay, so does this help us explain the answer? We're going to write this down first. So NH3, okay, is held together by hydrogen bonding. Okay, while CH4 is held together by IDID attraction. So which one is stronger in this case? Okay, NH3 hydrogen bonds are stronger, right? So you just tell me that hydrogen bonds are stronger, which means what? Okay, so in this case, we are not explaining melting points or boiling points. We are explaining deviations from ideal behavior. So if hydrogen bonds in NH3 are stronger, that means what? Are the intermolecular forces more significant or more negligible? More significant, right? Okay, so take a look. So since they are stronger than the IDID attraction, okay, thus, if you're more significant, what does that mean? More ideal or less ideal? Okay, more, less ideal, right? Okay, good. Okay, just tell me it's less ideal and deviates more from ideal behavior. So that's the idea. Okay, you don't need to write the word significant in this case. If you want to, you can, but the idea of stronger just means significant. Okay, so if you're more significant, that means you're approaching a real gas, so you're less ideal, so you must deviate more. Okay, so the answer to this question, right, is just to compare the intermolecular forces. That's what is reflected on this graph here. Okay, sometimes they might ask you to draw the graph yourself. Okay, so that's how it looks like. You must follow this shape. It goes down and it goes up. Later, I'll explain what this shape means. Now, I just need you to know how to compare. All right. So, let me try another example. So, once you're done with this, right, I need you to copy down the second graph and explain it yourself. Right. Okay, so this next question that we have, three guesses. I tell you guys who deviates the most and the least. Your job is to find a suitable explanation for these three guys. Okay, so give this a try. Again, your question is simple. Just explain the deviations of these three guesses. Okay, so PV over RT, right, against P, the graph is a straight line because just now we assume that PV equals to nRT, right? The number of moles of these gases is the same. So because number of moles is the same, I just shift everything to the other side. Okay, so that's why a lot of the times for this question, right, they'll plot PV over RT because it's equal to N, and you know N is constant. So this entire expression must remain as a constant if number of moles is the same. Yeah, okay. As in the reason why it deviates like that, right? I'll explain later. Now your job is to compare which one deviates more first. That's why that's our first thing, just to compare. Sorry? R is a constant also, but oftentimes, I know this can be ignored here, right? But oftentimes they also place it into the graph. Lah. Yeah, okay, so we just follow the convention. Lah. Yeah, not that it matters. You can remove the R, it's still the same graph. Yeah, so that's for this. Okay, so again, your task over here is to compare three guys now instead of two guys. I told you guys who deviates the most and the least already. Your job is to find any explanation here that is suitable to explain these three guys. Okay, so slowly go and try it. All right. Compare one at a time first. Okay, so you should have like two paragraphs. Okay, the first one is to compare these two. Second paragraph is to compare this last guy. Something like that. Right? Along the same lines as what we have just done. So it shouldn't be a big problem. Yeah, that's why I say today's lesson has a lot more relation to camp bonding stuff. Last lesson was a chill session because it's just ideal gas equation. Who? Huh? Who complained? I haven't gone through this part yet though. The which one? Oh, okay. Oh, really? Yeah. Okay. I see, I see. Okay, lah, but this one's more chem. Today's one's more chemistry. Yeah. 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 Because pH, you can go and count the M. It's way bigger. Data booklet, is it? Okay, I'll just tell you what you need to know. I'm like a portable data booklet. Okay. Okay, okay. So yeah, the thought process is correct. You consider whether they are comparable first. If the answer is yes, you talk about it. The answer is no, like the previous question, then don't talk about it. No? Mm. No. Never say that, just compare. Go straight. You can, but you won't get extra marks. You're wasting your time. Yeah, okay, go straight into comparing. Yeah, I realize a lot of people like to do that. No, not necessary. Instead of you need more paper, go take some more. Give you one more paper. Because we still have more to draw. Yeah, we're gonna write the first paragraph first. Yeah. Yep, exactly. Okay, so this is the first explanation. Okay, comparing Cl2 against CH4. Right? So the first thing that I noticed, right, that both of them are non-polar. So I compare the electron cloud size. Cl2 is clearly larger. Larger means more easily polarized, stronger ID-ID attractions. So that right there is a chem bonding concept, right? Having stronger intermolecular forces already means it is more significant, right? So it points to the fact that it is less ideal. So that's the first explanation. The second explanation is that it also has this that we can talk about, right? We know that since it's larger, that means it's literally larger, like it has a larger molecular size. If you have a larger size, that means it makes sense that it occupies a larger volume in the container, right? Okay, it's a very simple idea. If you can't see it, you can draw two separate containers. Okay, we know Cl2 is much larger, so larger occupies more space in the container. Okay, whereas PH4 is a lot smaller. So smaller means they occupy less space in the container. Okay, so in other words, having a larger molecular size means you have more significant volume compared to the container. Okay, yes. I mean, rightfully is always write the full thing, but in exam, right, it's more optimal if you write IDID. Yeah. And unless your teacher is very particular over it, then I'm sorry, lah. You just got an unlucky teacher. Okay, but anyways, can see this idea here? Having a larger molecular size means it occupies a more significant volume of the container. Okay, it's like you have three fat people in the room versus three skinny people in the room. Who occupies more space? Definitely the fat people. Right? Okay, so that's the idea here. You talk about both, you touch on them, don't explain too much. Okay, then now we also want to explain the last guy, which is HCl. Okay, so let's see, guys. How do we explain HCl? We look through the logic first before I write the explanation. How do we do HCl? Okay, we compare HCl to Cl2. This guy deviates more than Cl2, right? Have we used size as a comparison? No, because clearly HCl has a smaller size than Cl2, right? So we can't use a larger electron cloud size as the reason. We also can't say there's a larger volume, right? Okay, it doesn't occupy that much space in the container compared to Cl2. So that means what else can we use to explain? We can't use volume. We can't use IDID. Anything else? PDPD, exactly. We know that intermolecular forces can compare a lot of different things, right? So we know that HCl is PDPD, Cl2 is just IDID, who is stronger? PDPD. So you're seeing what we do here. We are finding a suitable explanation for this question. Okay, we dig until we find the correct explanation. So you tell me HCl is held together by PDPD attractions. Okay, which are stronger than the IDID attractions in Cl2. Since it has more significant interactions, it's going to deviate more. So you tell me HCl is less ideal than Cl2, so it deviates the most. You can use absolute words like least ideal, or you want to put less ideal can like compared to the other guys, Cl2. Okay, or you can say deviates the most. So it always relates to the assumptions. Okay, the assumptions tell you whether something is more ideal or less ideal. Okay, that's how you compare the deviation. So that's the first part of our segment here done. Okay, a rather easy question type, honestly. It is honestly quite simple. In the next part, right, explaining the shape. Now, usually our schools don't really teach this except for Raffles and maybe EJs. So that's why shape is something I need to go through with you guys. Okay, but despite everything, I'll just teach everyone the shape. It doesn't matter the school. But I'm just saying that Raffles usually does this. Okay, so I'll explain how the shape works. Okay, this is a little bit harder to explain because it does lean into the physics context. Okay, but never mind. It's still within the scope of what we've done. So any final questions with comparing so far? No, okay, so perhaps, okay, we're going to draw another graph once again. Okay, but this time around, we need to talk about the shape. I think the main question is, why does it go down before going up? So for now, can you all draw another one of these graphs, but just draw like NH3, for example, just a real guess. So something like this. Okay, so yeah, that's what we're going to compare now. Just draw one graph. So the ideal gas is flat. Real gas has this very specific curve. Looks like a Nike symbol, right? And the main thing is, let's annotate this graph a little bit, right? There's this part where it intersects with the ideal gas line. So we're going to use that as like the barrier between the two sides, okay? On the left-hand side of this, we have low external pressure. Okay, so keep in mind, right, it's the same thing as what we did earlier. I'm talking about external pressure. So this P here refers to the pressure on the outside on the container. Make sense? So I say again, this is the container. We are talking about the pressure exerted from the outside, not the pressure of the gas within. Okay, so I established that first. I'll go through this in a bit again. And then after this point, it's high external pressure. Okay, can. Next thing I need you to indicate, this part of the graph here is called negative deviation. It's just a fancy term. It just means it deviates downwards. So you have to take note of PV over RT in this case is a value of 1 for an ideal gas. Okay, but then it deviates downwards below 1, so it's called negative deviation. Then up here, right? Okay, clearly it's positive deviation. Our job is to explain one thing. For all real gases, okay, there are exceptions, but just hear me out first. Okay, for most real gases, doesn't matter NH3, CH4, or whatever gases that I gave you just now, all of them have this Nike symbol. So why does it deviate negatively at low external pressure, but deviate positively at high external pressure? You can see that. Okay, so that's what we're trying to explain. So first, let's start off with low external pressure. Okay, now do you remember something, right? When we have low external pressure, what is this? Earlier, what did we discuss? Okay, so imagine this low external pressure once again. I'll just draw the same diagram as just now. That means you're not really pressing the outside of the container that much. But high external pressure means what? It means you press the container until it becomes damn small, right? You can see that. So imagine this, you press until it's very small. Okay, so imagine I have only like 4 gas molecules. These four gas molecules are here versus they are here. So can I ask you guys, right, which one occupies a larger volume of the container? High or low? Actually, it should be high. Okay, because just now you missed the analogy lah. Okay, imagine the three of us are in this classroom. Are we occupying a lot of space in this classroom? Honestly, we're not occupying a lot of space, right? Okay, but imagine the three of us are now squeezed into the toilet. Are we occupying a lot of space in that toilet? Yes. So the idea is that it's always relative to your container. That's why the word container here is very important. You cannot miss this out. Okay? We all occupy the same space objectively, but it's the room that is relative to us, right? Or we are relative to the room. So as you can see, let's see this again. Low external pressure over here, right? Negligible or significant volume compared to the container. Negligible, right? Okay, they don't take up a large portion at all. So we're going to write this down. Same thing as what we wrote just now. Volume of molecules is negligible compared to the volume of the container. Now this is whatever we wrote earlier, so there's nothing new here. I'm just like parroting whatever I talked about just now. So guys, I ask you a question, a very simple question. If the volume is negligible, right? Can we use this to explain any sort of deviation? Okay, hear me out. Okay, hear me out first. Negligible means is it ideal or real? If the volume is negligible. Negligible means it's explaining ideal behavior, right? But we are now trying to explain why it deviates. Deviates means it's ideal or real. Real. Does this explain that then? No, because this is pointing towards the fact that the gas is ideal. It doesn't allow us to explain why it deviates, why it's a real gas. So that's why, right, if the volume we cannot explain, then what can we use to explain instead? If we can't use volume in this case, we talk about, there's only two, right? If we can't talk about volume, we talk about intermolecular forces. Okay, guys, real gases, do they have intermolecular forces? Have, okay? Ideal gases don't have intermolecular force. Real gases do. So we use intermolecular force to explain here. Okay, so guys, think about it. The intermolecular forces between the molecules, what would this cause? Okay, what would this cause? Okay, it will cause. Okay, so that's what we're gonna explain now. Just follow me on this. Okay, but clear so far. Okay, before I move on to the next analogy, you all understand at low external pressure, volume is negligible. That points to the fact that it's ideal, but clearly this is not ideal, it's real. Right? Okay, so we can't use volume to explain, we look at intermolecular force. Now let's move on to the explanation. Okay, guys, imagine there's a wall. Now this wall over here, right? Imagine there's a person running towards it. Okay, he's gonna crash into the wall and it will hurt him, right? Okay, but now imagine another scenario where there's the same wall and the same person running towards this wall. However, this time around, right, there is an elastic band and he's getting held back by his friend. He's like, okay, no, don't run towards the wall. So guys, can I tell you, in which scenario does a person hit the wall softer? The second one, because there's an elastic band holding him back, right? So he can't run at the wall with enough force. So now, relate it back to a gas molecule. Guys, This is an ideal gas particle. Ideal gas particles, do they have intermolecular forces? No, right? So they can just whack the wall at full force. However, over here, this represents a real gas molecule. Do they have intermolecular forces? Yes. And because they have intermolecular forces, will they hit the wall with more force or less force? Less force. So guys, which one the pressure is lower? Ideal or real? Which one is lower pressure? Real. Because you don't hit the wall as hard, right? That's the idea of pressure. So the intermolecular forces between molecules will cause the real gas pressure to be higher or lower than the ideal gas pressure. Okay. Lower or higher? Lower. Can see what I'm doing here. Ideal has no intermolecular force, pressure very high. But pressure of a real gas is lower. So guys, I ask you, come back to the y-axis. PV over RT. Is it more than 1 or less than 1? If the pressure of a real gas is lower, so it's less than 1. Can you see that? The pressure of a real gas is lower, so it's less than 1. Guys, is this positive or negative deviation? Negative. So I need you to write this down now. Okay. Negative deviation occurs because of intermolecular forces. I always think of the analogy, okay, of someone with an elastic band pulling you back. Okay. So I say again, this is the most important thing. Negative deviation of the graph, right, is because of intermolecular forces. You cannot explain volume here because, as I already mentioned, low pressure, right, the volume is negligible. It doesn't explain shit. That's why we can only turn to the other explanation, which is intermolecular forces. Does this make sense so far? Okay. So the graph, you need to understand how this works. This shape is not easy to understand. Okay, hopefully the analogy y'all can write down also. Okay. Okay, so if you want to draw the analogy, I'll draw again for you guys. Ideal gas, no intermolecular forces. So the gas particles are just separate, right? You want to whack the wall, you whack it at full force. Okay, but a real gas has intermolecular forces. So those attractions, right, will prevent it from whacking the wall with full force, basically. Okay. So maybe I can draw 3 arrows here to show that it really whacks the wall. But this one, right, 1 arrow to show that it doesn't hit the wall as hard. So once again, lower pressure. That's why the fraction here is lower if I goes down. Makes sense so far? Right? So internalize this. Okay, because in MCQ, they can ask you, right, which part of the graph is explained using intermolecular forces. They must tell me the negative part of the graph. So you tell me the positive wrong. Right? Okay, there's only one part of the graph. We will move on to positive deviation. All right, first, I'm going to give my throat a break. This is like my COVID sore throat. I don't think you'll experience the COVID sore throat. You have, I know the rest do it. You're lucky. Because the COVID sore throat is a needle poking at your throat. It's exactly what this feels like, but it's not COVID. It's like the flu bug. Huh? You feel more itchy. Don't no, now what's going on? I got the sore. Wow, the sore throat is painful. Oof. Okay, can so far. Okay, so high pressure. Okay, let's move on to high pressure. Okay, why does it deviate positively now? Right. Do you remember earlier when I discussed high pressure, right? The volume is it negligible or significant? Okay, look at this. The pressure on the outside very high, right? It's like us being squeezed into that small little toilet here. So are we occupying a lot of space in that toilet? Yes. Okay, so that means the volume of molecules is significant. But if you just put here significant, right, it's wrong. Because I already told you guys, it compared to the place you are located in. Three of us occupy the same space no matter where we go. But compared to the different rooms, okay, it depends, it is the proportion, right? Okay, in the classroom, we occupy less space. In the toilet, we occupy more space. Okay, so volume of particles significant, must add on this word, never be lazy. If you're lazy, never write the last few words, I'm sorry, the whole thing is wrong. Okay, compared to the volume of the container. Okay, guys, can I now use volume to discuss deviation? Just now I cannot because it's ideal, right? It explains ideal, so I can't use that to explain, but now it can. So we explain using volume. Okay, so since it is significant, okay, so sure, let's explain volume now. Now, guys, the volume of a real gas, is it larger or smaller than the volume of an ideal gas? No, it's like simple. Larger. Why? Because of the fact that ideal gases have no size, right? But then real gases have size. So no shit is larger, right? It has to occupy more space, definitely. Okay, if you want another picture, I can show you another picture. A real gas, right, has actual size, so it occupies space. Okay, but then okay, I know it's very hard to draw ideal gas because ideal gases are like no size. I know this is size, but you can already see this occupies more space. So the volume it occupies is more. So guys, I ask you again, the PV over RT is more than one or less than one of a real gas? Real gas has higher volume, so it's more than one, right? What kind of deviation is it? Positive deviation. And then you have to take note, right? Positive deviation is due to significant volume. So once again, if the question asks you at which point on this graph has significant volume being the most important factor, you must tell me anything above this basically this part of the graph. If they ask you which one has the most significant intermolecular force, you must point me towards the negative deviation part. Okay, that's how they test the MCQ. Okay, can let me just remove this. There's one thing that you guys might be asking me. Here I explain using volume, right? Can I explain using intermolecular forces? So let's consider. Here, I can explain using intermolecular force, but not volume, because volume is ideal, right? Here, we can explain using volume, but let's consider, can we explain using intermolecular force? I ask you all, when you're very close with each other like that, imagine we three squeeze in the toy. When we are very close like this, right? We have intermolecular forces. Is it significant? It seems significant, right? Because you're very close to each other. Agree? Compared to over here. Now, you see, us in the room, we are so far apart from each other. But in the toilet, we are very close. You might think that's intermolecular force, right? So can we explain using intermolecular force? Answer is no. Why? Okay, imagine the toilet really very, very small. We are like side by side, shoulder, shoulder. We can't even move our hands. We can't even breathe. Will you still want to attract each other closer to yourself in that scenario? In a very claustrophobic environment, you wouldn't ask the person to come closer towards you. What will you tell the person? Can you move? Right? Can you go away? So guys, that's what happens in molecules also. In the molecular world, if they are so high pressure squeezed together, they will actually have intermolecular repulsions. Okay, I want you to take note of this also. Okay, so maybe you can write here. Cannot use intermolecular forces of attraction to explain it as there is intermolecular repulsion instead, or there are intermolecular repulsions. So I'm just telling all this to gain a better understanding of the whole picture. Okay? That means low and high external pressure, you only have one factor to explain. Here cannot use attraction. A cannot. Okay, because there's repulsion. If you're that close to your to the other molecules, you wouldn't attract the thing. They'll actually repel. Okay. So yeah, this shape thing takes some time to understand it. Okay, your job is to understand why it goes down and goes up. Sometimes, occasionally, they will test, but take note, guys. Mostly they'll test on the deviations, the comparing who deviates more, who deviates less, and so far. You have one last thing to go through. Okay, but so far, any questions? Okay, can. Let me repeat that part. I think that's important enough. Okay, take a look. If they ask you guys, which point on this graph is intermolecular forces the most significant reason for the deviation? Which part will it be? Okay, basically this part of the graph had negative deviation. Okay, at which point on the graph is volume the most important reason for the deviation? And which part of the graph is it? This part here. Okay, basically you just need to take notice. Whatever the question asks you, if it asks intermolecular force, choose negative deviation. If it asks volume, you choose the positive part. Yeah, that's what they say here. Those questions are rare. I try my best to go and find some for you guys. Okay, but they are rare for a reason because other schools don't really test this. Your school occasionally does. But when the question comes, it's very obvious. Okay, can? Yeah. Okay, with that said, we still have one more thing to go through. Just now I said, most graphs, not all, most graphs have this Nike shape, right? But there's one exception, and you need to know this. Okay, so I'm going to remove this. You might want to draw another one of these graphs. But this time around, we're going to talk about hydrogen and helium. Okay, take note of these two graphs. Hydrogen and helium. Okay. Hydrogen and helium, right? The deviation looks like that. Either hydrogen or helium. You must know. This one must know. Right. Okay, so the exception to the shape. Okay, take note of hydrogen and helium. So in an exam, if they ask you guys to sketch the deviation graph for hydrogen or helium, I need to see a nice little straight line like this, a diagonally straight line. We will explain why, but I won't go into too much detail because the real reason behind it is out of our syllabus. Okay? So I'll just teach you guys not from a science perspective, but from a logic perspective. You just look at what we're going to do in a bit. Okay? Now, our job here is to ask one question. Why does hydrogen or helium deviate positively at low external pressure? Okay, you notice one thing, high external pressure, both of them are deviating positively, right? So I don't really have to explain this because we explained this for, it's true for all gases. Even hydrogen and helium, all gases at high external pressure will be positively deviated. The only thing that we need to explain is at low external pressure, why is it that these two guys must deviate positively? It should be negative, right? For normal gas, it should be negative, but why is it positive here? Okay, very good. Okay, so you notice something, guys. Just now I mentioned negative deviations because of good. Negative deviation is due to the fact that the molecules have significant, again, IMFA. But what's the problem with hydrogen and helium? What do you mention also? So very good. Okay, so the thing about hydrogen and helium is that they have very, very weak intermolecular forces. Yes, okay, small electron cloud size, all that. Fundamental idea is that their intermolecular force is so weak. So guys, logic here, significant intermolecular force deviate negatively. So if very weak intermolecular force means what? Deviate positively. Can see why? I say again, the reason why gases deviate negatively, just now we mentioned already, is because of significant intermolecular forces. But hydrogen and helium don't have that at all. They're so small. Intermolecular force so weak. So we flip it around. Since it's weak, right, it should have positive deviation. Yeah, I know this is not a very convincing argument, but again, this is all purely based on logic. I tell you what you all need to do. You all just need to know the shape. Just draw one straight line for this. If you want to know why, I will just tell you this up until here. The reason why I won't tell you about the rest is because the real explanation lies behind this idea called compressibility factor, which I'll not go through. This one I'm also not very sure because it's very physics concept already. Okay, that's the real explanation. You can go read up on it if you want. I've tried myself. It's a bit confusing, so I suggest you don't. You know? So shape of the graph, challenging. Take some time to digest this idea, but we are pretty much done with the shape. Okay. Okay. Okay, so of course you can staple these at the back of your paper. Yeah, at the back of the notes. The notes are not wrong or anything else, but I'm just adding on more stuff. So anyways, yeah. Okay, we shall take a break first. Okay, then later we will I hope you have the tutorial if you guys have, right? Yeah, the tutorial later we will study. Yeah, okay, now we just take a break first. Later we just try questions. Yeah, okay. Hello. Okay, so we're gonna continue with the tutorial. Okay, today we're gonna try a few questions. In the next lesson, right? Next lesson, I don't move on to energetics yet. Okay, I will do another round of revision. So gaseous state plus other stuff. Probably gaseous state because I probably won't touch gaseous state that much ever again, honestly. Okay, maybe in June once. So now let's just do a few questions. Next lesson, we'll focus on more questions. Okay, so for now, right, I want you guys to take a look at level 1 questions. We're going to do question 4 and 5. So if you're finished with 4, you can move on to 5. But if not, you can just go at your own pace. Okay, we're going to start with some of the questions that we did last session. Okay. Yeah, look at the scenario carefully. Okay, so see some of you are just subbing values into the ideal gas equation, which is not actually the case for here. Yeah, okay, so let me just discuss something first. Okay, if you all look at this scenario, they talk about a balloon, right? A balloon has this amount of air at 5 degrees, and then they transfer it to 25 degrees. Okay, so guys, let's just identify all constants first. Now, subbing in values, PV girls and NRT will not get us anywhere, right? Okay, because first of all, guys, what's constant here? Which variable? Okay, so they mentioned at, okay, the balloon is the same balloon, right? So the number of moles will be the same, are the same. Okay, your pressure is the same because they say so, right? So guys, what are we actually comparing in this question? Volume and temperature. Okay, so exactly, it's volume directly proportional to temperature. And one thing we can do, right? Okay, maybe if you don't want to write this, it's fine. But I highly suggest you guys push all your constants to one side and then the rest to the other side. So over here, it will be V over T equals to NR over P. Now, the reason why we do this is because the entirety of the right-hand side is a constant. In other words, V over T is equals to a constant. You can see that? So remember, what's this equation that we're going to use here? You all notice, right, that there's a before and after scenario. Before is placed in a 5-degree place, then afterwards 25 degrees is in the house. So guys, if there's a before and after scenario, do you all remember V over T is a constant, meaning V1 over T1 must be equal to V2 over T2. This is how you derive this formula over here first. So what we are looking for is not stubbing in values into the equation. That one will get you nowhere. Okay, here's about before and after scenario, as you can clearly see. So they want you to find a new volume, so just do that over here. Right? So just repeating the same thing for part B as well. Okay, so once again, I'll push all your constants to one side, then you can get the left side that changes. But no matter how they change, the V over T value must be the same. Okay, once you're done with question 4, you can move on to question 5. I'll write the answer on the board in just a moment. Okay. First answer here should be 1.05 dm cube. It must tell me it's more than 1 dm cube. And just tell me that the balloon will burst. Okay, so guys, this question, they're not asking for the value, they're asking for a conclusion that's backed by your value. So take note, right? This is how you express it very quickly. Don't go and write a statement. The statement wastes you a lot of time. Okay, just tell me this, compare, inequality sign, very fast one. Okay. It's 1.045, but I round it up to 1.45. You didn't get it? High chance you did a calculation error here. So look at this, yeah, wrong already. Temperature must be what? Oh. Guys, please take note, temperature must be in Kelvin, always. This is in degrees Celsius, 100% wrong. Okay. Like the question say 5 degrees Celsius and 25 degrees Celsius. Can I just ask you guys, is 25 degrees Celsius 5 times as hot as 25? Sorry, is 25 5 times as hot as 5? No, it's not. Guys, please take note. Degree Celsius is just it is not the most accurate way to measure temperature. Remember, you need to plus 273 to each. So that means in Kelvin is 278 and 298. Guys, now you look at it again. Is this 5 times hotter? No, it's not. Okay, so always convert to Kelvin, right? It's not correct to say 5 times as hot. Okay, I think because our daily life, we use degrees Celsius too much. Okay, repeat the same thing for part B. Part B, make sure you also identify all the variables that change. And once you're done, you can move on to question 5. Okay, so for question 4, part B, I hope you all realize that your pressure, volume, and temperature are all changing. You just have to read through the question and see what variables are changing yourself. Then you derive this expression here. Okay, your number of moles is the same because they already said the sample of gas, the number of moles never change. You're just transferring the gas to another container. Okay, but the container has different temperature, different volume, different temperature. Pressure, sorry. Okay, so you just sub in the values here. Okay, this is what you should get. They ask you to find the final temperature, right? So T2 is 327.6 Kelvin. But the question further asks you guys for the change in temperature. So this is not your final answer yet. Change in temperature, it's 54.6 Kelvin. No, 327.6, because this is not the final answer yet. If it's not the final answer, it has to be at least 4 SF. If not, you have truncation error. Okay, then the change in temperature will be 54.6. Then there's 3SF. Okay, and that's 54.6 Kelvin, right? How do I convert this to degrees Celsius? Okay, minus 273. Okay, I want you to take note of one thing. The change in temperature here, isn't it also 54.6 degrees Celsius? Can you all see why? Because guys, I need you all to understand this is the change in temperature. Even if you convert the initial and final temperatures to degrees Celsius, you minus off, right? The change will be the same one. Okay, so that's something I need you all to take note of. Okay, the only time where degrees Celsius and Kelvin are the same is if it's the change in temperature. Very simple example is 1 degree Celsius to 5 degrees Celsius is a change of 4 degrees. But even if you convert each degree Celsius to Kelvin, so this 274 Kelvin, this is 278 Kelvin, you notice both of them, right? The change in temperature is 4 Kelvin or 4 degrees Celsius. The same. So take note of that from now on. If they ask you to express it in degrees Celsius, don't suddenly go and convert by minusing 273 because this is a change in temperature. Okay, and so if that's it, okay, I need you all to try question 5. Any other questions here? Calculation, any problem? If okay, right, you can just flip over to the next page. You give the graph question a try. Okay. Very good. Why? One more come. Come, I take a look. Oh, yeah. You know, if you're finding T2, the temperature after you change it to another container, right? The initial temperature is not 327.6. Initial temperature is 0 degrees, which is only 273. What I'm finding here is the after temperature. Yeah, it 273, not 32. Yeah. Then calculate again, 3 lah. Yeah, about 2 more minutes. Now I'm gonna go through this question. Okay, we did a whole bunch of graphs last lesson. So same idea here. Okay, 1 more minute. Okay, come, let's go through this question because we have a few others we want to try also, right? Okay, guys, when you're given this graph question, very common in MCQ. Okay, first things first, you must look at the options. Okay, let's look at the first option and see, just check. Right, there are two things you need to check for in these set of questions. You need to go and take down also. Okay, the first thing you need to check for is the shape of the graph. Okay, fundamentally, if the shape is wrong, right, then you don't even need to consider anything else. Okay, but once the shape is correct, you also need to check the comparison, which one of the two graphs is ranked properly. Okay, so that's like what I call the third variable. The third variable must be placed correctly, must be explained correctly in the graph. So I remember going through this with you guys last lesson, right? Where you have two, or you have two different graphs like this, meaning to say you have three variables to compare. Okay, I and J have different MRs. So MR is one variable, PV is another variable, P is a third variable. So there's so many variables here, we need to compare. So guys, if you look at this A, right, A and B are pretty much the same thing. The only difference is I and J are swapped. Okay, so are these correct? Is A and B correct? Guys, we look at the shape first. Is the shape of A and B correct? Answer is no. Okay, I hope you all understand that this graph should be a vertical shape. If you plot a graph of P and PV, it should be vertical. Okay, we mentioned last lesson, right, that PV should be a constant value. Constant doesn't mean horizontal. Constant means PV is constant. So that's why it has to be one value on the x-axis that has to be constant. Does that make sense? So, okay, because over here, you look at the PV equals the nRT equation. In this question, we have, okay, they said fixed masses, right? Okay, is there mass in this equation currently? No. Okay, so why not we go and include mass inside, which is, how do we include mass into the equation? MRT over MR. Okay, so that's what we discussed, right? My throat and pain, I cannot speak loud. Okay, so can, in other words, okay, we check fixed matter to M is constant, right? How about R? R is constant. Temperature, they say is constant, right? What else? Okay, so you notice that's it. Okay, so PV and MR. So MR is two different graphs, right? But you look at the shape of one graph first. So that means MR should, we don't care about MR in this case, or just one graph, right? PV should be equal to a constant, right? Since the whole of the right hand side is constant. So when P increases, what will happen to V? It will decrease such that the product still remains constant. That's why it's constant value. That's what we explained last lesson. No? Yeah, okay, but here because it's MR, right? MR is different. That's why it's two starting points of the graph. And anyways, the graph for A and B is wrong. Okay, so what we have is C and D. Agree? So C and D are the shapes, correct? We identify again. So PV equals the nRT, right? Okay, so take a look, right? They said constant P, correct? So P is constant, N is constant, R is constant. We are basically comparing V and T. So V and T are directly proportional. This shape is correct. Okay? So shape is correct for C and D. The only thing we need to do left is to check I and J, right? Yeah, which one is in the correct order. So do you all remember what's the solution to having three variables? What should I do? Okay, so yeah, in this case, I need to bring back this equation because now the MR is also different, right? So why not I bring that back? So PV equals to MRT over MR. Once again, mass is constant, R is constant, temperature is constant, sorry, temperature is not constant, your pressure is constant. You see that? Okay, we have three variables, right? And it's not possible for us to compare three variables. So what should we do? Okay, what should we do over here? You remember, the solution is to make one of them constant, right? By drawing a vertical line intersecting both graphs. Because by doing this, what am I doing? What am I making constant? Temperature constant. That's why temperature is constant. Now I'm comparing V and MR. So what's the relationship? V is inversely proportional to MR. With two variables, the higher the V, the lower the MR. The higher the V, the lower the MR. The lower the V, the higher the MR. Is it correct? Yes. So the answer here B, C. D is just the opposite, so that means I was wrong. Okay, can solve these kind of questions. In the shape you settle already, you can settle the third variable by drawing a vertical line such that out of the three variables, one of them is made constant. Okay, can. Mm. Which one? Sorry. Mm.
And then I get
1 over mr equals to b over t. So t you put the other side. Okay, can as well. Because b and t are variables that you can. Sorry? Yeah.
that's the F1 over
Wait, hold on. Yeah, yes, correct. Okay, yeah, that makes sense as well. Okay, so what you're doing is, you see this equation, right? What you did, right, is that you are dividing by t on both sides, right? Okay, because t initially is not constant before you draw the vertical line. So you divide by t, so it becomes b over t, not equals as proportional to 1 over mr. The reason why it's not equal is because equals means you have all these other constants inside. So if you want to remove all these constants, you must change it to a proportion. Okay, but again, you will still arrive at this because I draw a vertical line. Essentially, t is now a constant. So that's why v proportional to 1 over mr. Okay, this works as well. Right. Yeah. Okay, good. Can I? You will definitely practice more of this. That's why I feel that there's another lesson for this school. Okay, let's try more questions. I want you to try, I think 8 and 9, if I'm not wrong. Yeah, 8 and 9. These are questions related to what we did today. Right? So now level 1, 8 and 9. Okay, rather important question. Yeah, next week, correct. Is it next week? Wait, no, not next week. The following week. Bridge. Oh, hockey also. Oh, no, next following week. Because next week I still need to catch up one more thing. Yeah, following week. Sorry? Who? IB. Who is IB? Oh no, we're referring to IB, is it? Ah, IB. You probably don't know her. She's O-level student. IB, who's IB? Never seen before. Perhaps you'll try question 8 first, then we go through. Okay, don't need to move on to question 9 yet. Later we move on to 9 together. Right. In like 30 more seconds. Okay, let's explain question 8. Okay, question 8 is very vague, but once you can capture the concept of this question, you can answer it very easily. So guys, let's present the scenario first. They tell you the pressure, temperature, number of moles, but they got different volume. Okay, do you all notice something? When you do PV equals to nRT, they only gave you one pressure, one temperature, one N, and the R is the same, right? So if that's the case, that means your volume should only be one value, right? What's the value of D? If you actually calculated the volume in this equation, what's the answer? You'll get it? Okay, so let me spare you all the trouble. If you sub in all these values into the equation, your volume is actually 16.7 dm. Now, what does this volume represent? The volume of what kind of gas? Ideal gas. Good. Okay, because you're using the ideal gas equation. So let's write this down. The volume of an ideal gas is 16.7 dm cubed at these conditions. And based on that alone, guys, what does that tell you about gas Y? Okay, first of all, what does that tell you about gas X? Okay, it's close to ideal, right? Okay, so we shouldn't say ideal because gas X and Y are both real, but which one is more ideal? X, because it's closer towards this value of 16.7. So go and write this down. For gas X, right, the volume of X is pretty much the same as the volume of an ideal gas. So there's very little deviation. Okay, very ideal. On the other hand, the volume of gas Y is a lot larger than the volume of an ideal gas, right? So what does that tell you? Okay, what does that tell you? Volume Y is more ideal or less ideal than X? Less ideal because it deviates more from the value of 16.7. So we can infer from this information, this question is telling you that volume Y is less ideal or it also deviates more from volume X, which is the ideal volume. So then the option is basically asking you guys, choose the option that explains why volume Y or gas Y is less ideal. So which one's the answer here? Which one explains that Y is actually less ideal? Definitely not option A because that's just completely nonsense, right? Okay, how about B? Does B explain that Y is more ideal? No, right? Which one actually deviates more? NH3 or H2? NH3, because NH3 has stronger intermolecular forces. Hydrogen bonds, right? This is just ID. But also what? Other than having stronger intermolecular forces, NH3 is larger, right? It's a larger size, so definitely the volume of X is more significant. So this doesn't explain. Okay, we are looking at why. Why should be less ideal. Okay. So in that case, does option C allow us to explain that? Okay, can you tell me what's the explanation? Why is carbon dioxide less ideal than helium? Okay, it deviates more, yes. Okay, but why is that so? Carbon dioxide has larger electron cloud, which leads to stronger IDID. And larger electron cloud literally means it has more significant volume, right? Okay, more significant volume compared to the container. Can you all see that, right? So by saying all this, that means Y is less ideal, which is correct in this question. So you see, the question never just asks you, choose the option that explains that Y is less ideal. No, they want you to capture that information from the question. Now, I just want to talk about option D. Okay, so the answer here is C. Okay, but why is option D wrong? Guys, intermolecular forces explain what? You're, you're wrong already. Okay, intermolecular force explain negative deviations. Why are there negative deviations? Because the pressure of a real gas is higher or lower than an ideal gas. Remember the one where the guy is running towards the wall and then you're holding him back with a rubber band, right? It is less. So, in other words, option D explains pressure. It doesn't explain volume. You see that this question is different volume. If the question had different pressure, then option D might be the answer. Okay, so let's answer here. Okay, so with that, we're going to proceed over to question 9. 9 is also another deviation idea. Okay. Even if you're not sure, just make a smart guess here. Right. You'll notice a few things. They started off at a different point. One of them is twice as high. Okay, so that's only one of the things you can so far identify. I won't tell you about what you should be identifying also. Okay, go more stuff. You're okay with it? Okay, we discuss this slowly, because it's not an easy question on first glance. All right. Okay, so come, guys, okay, talk me through this. What do you notice in this graph here? I think the very first thing that you notice is very clearly they start at different points. Now, earlier, right, just now I tell you all that we start at the value of 1, correct? But here, clearly something is up such that the ideal gas line doesn't start at 1. Here, it is twice as high. How do we play with this? Okay, so first of all, you must clearly take out your PV equals NRT formula. And let's look at the question. Okay, what did they tell us? Okay, now I know they didn't tell us much. Okay, but you need to know how this graph comes about first, right? You should recognize an ideal gas, even though it's not drawn here, should have a PVP graph that's horizontal. But how do we arrive at this in the first place? So guys, I hope you all noticed something. Usually that straight line is observed if N, R, and T are constant, right? Because when these are constant, that means PV is equals to a constant value. So for ideal gas line, it will be horizontal. Make sense? Okay, but clearly, guys, the PV value is twice as high So what does that mean? If PV is twice as high. If this entire thing is twice as high, right, it could be because of what? If the left side is twice as high, it's because the right side could be twice as high, right? It could be the temperature twice as high, or number of moles twice as high. R is a constant still lah. So we have to consider either one of these things could have happened. That's why the value of PV on the left-hand side is twice as high. So put it 2 times as high number of moles or twice as high temperature. So guys, take a look at the first answer. Okay, we read out anything that's wrong first. Okay, so for the first question, correct, temperature twice as high, né? Wrong. Once again, guys, what's the trap that you guys just fell into? Is this really twice as high? No, never. Okay, if PV gets nRT, temperature must be in Kelvin. This is 298 Kelvin. This is 323 Kelvin. Now you look at it. Can you tell me with confidence that this is twice as high? No, okay, this is not, right? Okay, so this is out already. Okay, so same number of moles, and then the temperature is like 1 point something times high, so definitely will not be exactly twice like this. Okay, we've done this twice today already. Please be very careful. Okay, next. Option B. Does that make sense? Same temperature, okay? Okay, everything else here same temperature, so it doesn't matter. Moles twice as high. Could that work? It could work, right? Okay, so twice as high number of moles. Okay, it could work. How about option C? Could happen also, right? That's twice as high number of moles, twice as high PV. Okay, so B and C still in the still in our purview. Okay, how about D? Is D correct? Is the number of moles twice as high? No, okay, the B is actually half. So we know B is up, D is up. Make sense? Okay, so this is how you read out options in MCQ. You look at one factor first. The one factor that I'm looking at is the 2x and x. Anything that doesn't satisfy that, you will narrow down to a few options. Guys, then you ask yourself now, because B and C is about, both of them have twice as much PV, right? Your job now is to tell me what exactly is the difference between B and C. You'll notice it's the deviation. Good. Okay, the graph A and B, the deviations are different. Who deviates more? SO2. Correct. Okay, SO2 and H2. SO2 should deviate more because number one, what are the reasons? Why does SO2 deviate? It has stronger intermolecular forces and it is literally bigger, right? So it has a more significant volume. But so which one should it be? Which option? C. Because we know A can clearly deviate more than B, right? Okay, if A deviates more, so it should be SO2. Okay, very clearly, look at the shape, it's more curvy. So the answer here should be, sorry, C. Right? Yeah, C. Two factors in this question. Number one is the twice the value. Number two is the deviation. See that? It should so approach it like this. We'll definitely have more practice coming. Any questions so far? Okay, if there are no questions, that's it for today already. Next lesson, again, I'm doing more gaseous state questions, so bring a tutorial. I'll do questions not only from the tutorial, but also from other revision worksheets. Okay, then I'll probably have to assign homework from gaseous state also. You have to perfect gaseous state now, because the next time I'll touch this is in June. I won't make a mention of gaseous state until June holidays when we do a revision. That's why it's important, right? So you can see the work starts to pile up. So definitely try to catch up on your previous homework that I have given you guys. Yeah. Again, I'll mark it very, very soon because their mock test their test is over this week already. Yeah. Okay, so if that's the case, that's it for today.